Have you ever wondered what really lies above and below our solar system? Not in science fiction, but in the real universe, far beyond the planets, the solar system drifts through thin interstellar gas, quiet stellar neighborhoods, and the vast structure of the Milky Way itself, and inward. Everything leads back to the Sun, the star that holds it all together. In this video, space science takes a slow journey through the true layers of our cosmic surroundings. If this kind of calm space documentary is worth exploring, please like the video, subscribe to the channel, and share it with someone who loves the universe. The solar system rests in the Milky Way, far from the crowded center and far from the faintest outer edge. It lies within a minor spiral feature called the Orion Arm, sometimes called the Orion Spur, a smaller structure placed between two larger spiral arms known as Sagittarius and Perseus. This region is not empty, yet it is not dense. It holds stars, cold clouds of gas, grains of dust, and the faint remains of older stellar events. But each part is separated from the next by distances that are difficult to imagine in ordinary human terms. The Sun moves through this region as one star among many, following the broader rotation of the galaxy, while also carrying its own local motion through the nearby stellar neighborhood. From this wide setting, the solar system does not appear as a marked center or a special landmark. It is one small planetary system around one ordinary star. The Milky Way itself contains hundreds of billions of stars, and the Sun belongs to the quieter middle portion of that vast disk. This placement matters. The central parts of the galaxy are more crowded, with stronger gravitational disturbances, denser clouds, and more intense radiation from energetic objects. The far outer disk is thinner and poorer in the heavy elements that help build rocky worlds. The Sun occupies a middle ground where stars are present but not pressed tightly together, and where the material available for planets includes enough heavier elements, meaning chemical elements above hydrogen and helium, to form rock, metal, and ice. The Milky Way is a barred spiral galaxy. A bar is an elongated central structure made of stars, and spiral arms extend outward from that inner region. The Sun is not near the bar. It circles the galactic center at a distance of about 26,000 light-years. A light-year is the distance that light travels in 1 year, used here because ordinary measures become too small for galactic space. Even this large number does not place the solar system near the edge of the galaxy. The stellar disk extends much farther outward, and a much larger halo of sparse stars and dark matter surrounds the whole system. Dark matter is matter known through gravity rather than light. Observations show that it shapes the motions of galaxies, but its exact nature remains uncertain. Seen from far above, the Milky Way would show a broad rotating disk with curved arms, dark lanes of dust, and regions where new stars form inside giant molecular clouds. The solar system is not inside one of the brightest star-forming complexes. It is in a more settled zone, where the light of nearby stars is modest, and the larger structure of the galaxy unfolds at a calm distance. This does not mean the region is still. Every star is in motion. The Sun orbits the galactic center at roughly 220 kilometers per second, and one orbit takes about 230 million years. During the age of the Sun, it has completed only a small number of these galactic years. Around the solar system, the galaxy is shaped by layers of matter that are usually too thin to notice from within. There is the diffuse interstellar medium, meaning the gas and dust between stars. Most of it is extremely sparse. In many places, a volume the size of a room on Earth would contain far less matter than the best vacuum made in a laboratory. Yet over great distances, even thin material becomes important. It dims starlight, forms clouds, carries magnetic fields, and provides the raw material from which new stars eventually emerge. The Sun and its planets travel through this medium, enclosed within the larger galactic environment, while also generating a local bubble of solar influence much closer in. The stars nearest to the Sun belong to no tight cluster. The solar system is not part of a densely packed stellar family like a globular cluster, where stars crowd together in ancient swarms. It belongs instead to the galactic field, the ordinary background population of stars spread across the disk. These nearby stars differ in mass, age, brightness, and motion. Some are cool red dwarfs, small and long-lived stars that make up much of the galaxy's stellar population. Some are larger and brighter. Some travel in ways that show they formed in different places and only happen to pass through the same broad region now. The local galactic setting is therefore less like a city and more like an open plain with distant travellers, each following a path shaped by the galaxy's gravity. Above and below the solar system, in the most literal spatial sense, there is no fixed up or down in space itself, but there is a useful vertical direction relative to the flat plane of the Milky Way. The Sun sits close to the galactic midplane, the general central layer of the disk where many stars, gas clouds, and dust lanes are concentrated. It is not exactly on that plane. It lies slightly above it and moves in a gentle vertical oscillation over long spans of time, passing above and below the midplane as it continues its orbit around the galactic center. This motion is slow and natural, part of the way stars behave in a disk-shaped system. Above the plane, the density of gas and young stars declines. Below it, the same broad pattern continues. Farther away from the plane, the disk gives way to the more diffuse galactic halo, where stars are sparse and the structure becomes much thinner and less clouded by dust. This larger arrangement helps explain what is actually out there when the solar system is placed in context. It is not a ceiling of stars overhead and a separate floor beneath. It is a flattened galaxy, rich in structure along its disk and thinner in the vertical direction. Looking outward through the plane of the Milky Way reveals crowded star fields, bright nebulae, and dark dust lanes because the line of sight passes through a long path inside the disk. Looking away from the plane reveals fewer nearby obstructions and a darker, more open sky because the path leaves the dense stellar layer more quickly. The difference is real, but it belongs to galactic geometry rather than to any true cosmic up or down. The solar system therefore begins its story not as an isolated island, but as a small moving part inside a broad rotating disk of stars and diffuse matter. Its outermost context is galactic. Its home region is moderate, stable, and unremarkable in the best possible way. It is a place where long-lived stars can keep their planets for billions of years while circling through a changing but not violent neighborhood. In this wide first view, what lies above and below the solar system is the structure of the Milky Way itself, thinning away from the disk, while around it in all directions stretches the quiet, immense middle realm of one ordinary spiral galaxy. Beyond the immediate identity of the Milky Way, the solar system sits among nearby stars that are separated by extraordinary distances. In ordinary illustrations, stars are often shown close together so that they can fit within a frame, but the real arrangement is much more spacious. Around the Sun, the nearest stellar systems are not gathered in a bright cluster. They are spread through the local region of the galactic disk with wide gaps of cold, thin matter between them. The first clear fact about what is out there is therefore not crowding, but emptiness. The second is that this emptiness is not absolute. It contains light, magnetic fields, sparse gas, drifting dust, and the slow passage of stars moving under the gravity of the galaxy. The nearest star system to the Sun is Alpha Centauri, a group of stars about 4.3 light-years away. Within that system, Proxima Centauri is the closest single star to the solar system. Even this nearest known neighbour lies at a distance so large that sunlight, travelling faster than anything else known, still needs more than 4 years to cross it. Spacecraft built by human technology move far more slowly at those speeds. Travel to the nearest star would take many thousands of years. This is not because nearby stars are rare. It is because the scale between stars is vast. A planetary system may occupy a meaningful region around its own star. Yet between one star and the next there stretches an immense interval where no star shines from close range. This local stellar neighbourhood contains many red dwarfs. A red dwarf is a small, cool star that shines more dimly than the Sun and burns its fuel slowly. These stars are common in the galaxy, and many of the Sun's nearest neighbours belong to this class. Some are single stars. Some are part of pairs or larger groups. A few brighter stars stand out in the wider local region, but most nearby stars are modest in mass and faint in visible light. Their abundance helps define the true character of the solar system's surroundings. It is not enclosed by giant blue stars or crowded by extreme objects. It moves among quiet, ordinary stars, many of them much dimmer than the Sun, each with its own motion and possible retinue of planets. The distances between these stars remain difficult to hold in the mind because human experience is shaped by landscapes, oceans, and skies on one small world. Even the size of the solar system, when measured out to the farthest known planets and icy bodies, is tiny compared with the gap to another star. If the Sun were reduced to a small object held in the hand, Earth would orbit at a short distance nearby, and the outer planets would still remain within a modest area by comparison. The nearest star, under the same scale, would be placed far away across a large country or farther still, depending on the chosen model. These comparisons are only aids, but they reflect an important truth. A star system is not like a room inside a larger building. It is more like one lantern in a dark plane, with the next lantern set very far off. This spacing affects everything about the local environment. Gravity weakens with distance, so the Sun strongly controls its own planets and small bodies, but it does not dominate the stars beyond. Nearby stars influence the solar system only gently and over long periods, mainly at its most distant edges. Light, however, crosses those spaces freely. The night sky seen from Earth appears crowded with stars, yet this is a visual effect of depth. Bright points that seem side by side can actually lie at very different distances. Some of the stars visible in Earth's sky are tens of light-years away, others are hundreds. Their apparent closeness on a flat sky does not mean real nearness in space. The local neighbourhood also contains brown dwarfs, white dwarfs, and stars of varying ages. A brown dwarf is an object too small to sustain the steady hydrogen fusion that powers ordinary stars. It forms in a star-like way, but it does not shine with the long-lived stability of a true star. A white dwarf is the dense remnant left after a sun-like star ends its active life and sheds its outer layers. These objects add variety to the local region, though they are much less obvious to the eye than ordinary stars. Their presence shows that the nearby stellar population is not uniform. It records billions of years of galactic history through objects at different stages of existence. The Sun is also not at rest relative to its neighbours. Every nearby star has its own velocity and direction. Some slowly draw closer over long spans of time, others gradually recede. The pattern changes across millions of years. Constellations, which seem fixed in the short span of human life, are temporary arrangements. Their stars are not bound into stable pictures. They only happen to line up from one shifting viewpoint, in the far future or the deep past. The same stars form different patterns. This reminds the mind that the local neighbourhood is dynamic even when it appears still. The solar system passes through a moving company of stars, and no nearby arrangement remains forever unchanged. Most of the volume between these stars is filled not with large objects, but with the interstellar medium in its thinnest forms. This matter is so diffuse that it scarcely deserves the word cloud in the ordinary sense. Yet over long distances it matters greatly. It can absorb or scatter some wavelengths of light. It carries traces of atoms, ions, and molecules. It responds to magnetic fields and shock waves from ancient stellar explosions. Between nearby stars, the medium is often especially thin, part of a wider low-density region around the Sun. Still, it is present, and it means that the local neighbourhood is not an empty hole cut into nothing. It is a sparse physical environment through which the solar system travels. What lies above and below the solar system within this nearby stellar setting follows the same broad geometry already present in the galaxy. Along the galactic plane, more stars appear because the line of sight remains inside the denser disk. Away from that plane, the nearby stars thin out more quickly. The vertical direction relative to the disk leads into less crowded regions. Yet even there, the nearest stars remain part of a three-dimensional distribution. They surround the Sun in all directions, though not equally. The local map is therefore neither a shell nor a flat ring. It is a loose spatial field shaped by the larger disk of the Milky Way. This region can be described with a useful calmness. There is no immediate wall, no hidden upper layer packed with strange objects, no lower abyss directly beneath the solar system. There are simply neighbouring stars at different distances, most of them faint, all of them moving, with immense dark intervals between. Those intervals are not meaningless. They are the true substance of the local setting. They make clear that the solar system occupies a place of wide separation, where other suns exist, but far away, and where the nearest reality beyond its own boundary is not another world, but deep, cold, measured space. The solar system moves through a local patch of interstellar matter known as the local interstellar cloud. This cloud is not a dense or dark object in the familiar sense of the word cloud. It is a very thin region of gas, with a small amount of dust, spread across part of the nearby galactic environment. The Sun and its planets travel within it now. Observations indicate that this cloud is warm by interstellar standards, partly ionized and low in density. Ionized means that some atoms have lost electrons, so the gas carries electric charge in part rather than existing only as neutral atoms. Even with these features, the cloud remains so thin that any ordinary human image of fog, mist, or smoke would be far too thick to compare with it fairly. The existence of the local interstellar cloud becomes clear not through direct sight as a large glowing shape, but through careful measurement of light and particles. When starlight passes through interstellar gas, certain wavelengths are absorbed by atoms and ions along the way. These absorption features act like delicate marks in the light, revealing what material lies between the stars and Earth. By comparing many lines of sight toward nearby stars, astronomers trace the presence, speed, temperature, and composition of the thin gas around the solar system. Spacecraft also provide information by measuring the interaction between the Sun's outward flow and the material outside it. Together, these observations show that the solar system is not drifting through a vacuum without character. It is moving through a faint local environment with structure and properties that can be studied. This cloud belongs to a wider region of a low density around the Sun called the local bubble. The local bubble is a much larger cavity in the interstellar medium, likely shaped by ancient stellar explosions long ago. Within that broad cavity, the local interstellar cloud is one small denser patch. Other nearby cloudlets may also exist, and the exact arrangement of these structures remains an active area of study. Observations indicate that the local gas is not distributed as one perfect, simple form. Instead, it appears irregular, with changing density, motion, and temperature from place to place. The Sun happens to be inside one portion of this varied environment at the present time. The gas in the local interstellar cloud consists mainly of hydrogen and helium, the most common elements in the universe. There are also trace amounts of heavier elements, some in atomic form, some ionized, and some bound in dust grains. Hydrogen dominates much of interstellar space because it is the simplest and most abundant element. In the local cloud, some hydrogen remains neutral and some is ionized. This balance matters because neutral particles can drift deeper into the Sun's sphere of influence, while charged particles respond more strongly to magnetic fields and to the outward pressure of the solar wind. The cloud, therefore, is not only a background setting, it directly affects the outer shape and behavior of the heliosphere, the bubble made by the Sun's flowing particles. Temperature within the local interstellar cloud is measured in the range of several thousand degrees Kelvin, yet this does not imply heat in the ordinary bodily sense. In a gas this thin, temperature mainly describes the average energy of the particles rather than the presence of dense warmth like that of air in a room or water in a bath. A person placed in such a region would not feel surrounded by hot matter, because there are too few particles for heat to transfer in a familiar way. This is one of the quiet strangenesses of space. A region can be described as warm or even very hot by physical measurement, while still being almost empty in everyday terms. The cloud also carries a magnetic field, weak by terrestrial standards but important across large distances. Interstellar magnetic fields help guide charged particles, influence the motion of dust, and shape the boundaries where different flows of matter meet. The exact local field geometry is not known in complete detail, but observations indicate that it plays a meaningful role in the way the heliosphere is compressed or extended in different directions. This means that the cloud around the solar system is not merely a passive mist. Its motion, pressure, ionization, and magnetism all contribute to the larger interaction between the Sun and interstellar space. Dust in the local interstellar cloud is present only in small amounts, but its significance is greater than its mass might suggest. Dust grains are tiny solid particles made of materials such as silicates, carbon-rich compounds, and ices in some interstellar settings. In the local cloud, much of the dust is sparse and difficult to detect directly, yet some grains pass into the solar system. These grains can be measured by spacecraft instruments and can also affect how light is scattered and polarized. Dust offers a solid component in an environment otherwise dominated by gas, and it carries the chemical history of earlier stars that forged heavier elements and released them into space. The motion of the solar system through the local interstellar cloud is also part of the picture. The Sun is not waiting in place while the cloud drifts around it. Both the solar system and the surrounding interstellar material move within the Milky Way, and their relative motion creates a flow of interstellar gas past the outer boundary of the Sun's influence. This flow helps determine how neutral atoms enter the heliosphere and how the outer boundary is shaped. Measurements suggest a direction and speed for this incoming interstellar material, giving the local region a subtler symmetry. Space around the solar system is therefore not the same in every direction. It reflects the motion between the Sun and the cloud through which it passes. How long the Sun remains within this particular cloud is not known with full precision. Observations indicate that the local interstellar environment changes over long spans of time as the solar system moves onward and as small interstellar structures shift relative to one another. It remains uncertain exactly when the Sun entered the local interstellar cloud and how its surrounding environment may change in the future. What is known is more modest and more secure. The solar system is currently immersed in a thin stream of nearby interstellar gas, and this setting affects the boundary where the Sun meets the galaxy. Above and below the solar system, in the sense defined by the galactic plane, the local interstellar cloud does not form a hard layer or a simple ceiling and floor. It is part of a three-dimensional patchwork of nearby gas embedded within the wider local bubble. The cloud may extend unevenly in different directions, and its edges are not sharp in the way land or water boundaries are sharp on Earth. Instead, density changes gradually, and the cloud blends into neighbouring regions of different temperature and composition. This makes the local environment subtle. It is not announced by strong colour or clear shape. It is inferred through motion, absorption, particles, and pressure. The solar system, then, moves through a delicate region of real matter that is almost nothing by human standards and yet substantial on the scale of space. The local interstellar cloud is what actually surrounds the Sun just beyond its own outer domain. It is thin, warm, slightly charged, magnetized, and chemically simple, with traces of dust and structure that careful observation can reveal. In this region, the great emptiness between stars acquires a faint texture. It remains mostly dark and diffuse, but it is not blank. It has substance, and the solar system passes through it quietly. Around the solar system, the Sun creates a vast domain shaped not by solid walls or visible surfaces, but by a continuous outward flow of charged particles called the solar wind. This flow begins in the Sun's outer atmosphere and streams away in all directions, carrying energy, magnetic fields, and matter into surrounding space. Over great distances, it pushes against the thin interstellar material through which the solar system moves. The result is the heliosphere, a large bubble-like region where the Sun's influence remains stronger than the pressure of the nearby interstellar medium. It is not a perfect sphere, and it does not stand still. It shifts with solar activity and with the properties of the interstellar environment beyond it. Yet in broad terms, it forms the Sun's outer boundary region, the first great edge that defines what belongs to the solar system in a physical sense, rather than only in terms of gravity. The solar wind is made mainly of protons and electrons, with a smaller number of heavier ions. A proton is the positively charged particle found in the nucleus of a hydrogen atom, and an ion is an atom or molecule that carries electric charge. These particles leave the Sun at high speeds and spread outward through interplanetary space. Near Earth, the solar wind is already thin, but it still shapes the magnetic environment around planets and carries disturbances from solar eruptions. Far beyond the orbit of the major planets, it continues to flow, though it grows weaker as it expands across a larger volume. Even so, it does not simply fade into nothing. It keeps pressing outward until it encounters enough resistance from interstellar space to slow and change. The heliosphere is therefore not made from a single substance. It is formed by an interaction between two flows. One is the solar wind moving outward from the Sun. The other is the interstellar gas and magnetic field of the local cloud moving past the solar system, where the solar wind dominates. Space is filled with solar material and magnetic structure carried from the sun. Where interstellar influence dominates, the material belongs more to the galaxy beyond. Between these regimes lies a broad and complex boundary region. The heliosphere includes that whole outward reach of solar influence, from the inner planets to the far outer limits where the flow weakens and becomes compressed. This outer boundary region cannot be seen in ordinary light as a bright shell. It is traced through indirect measurements, especially by spacecraft. The Voyager probes provide the clearest direct evidence from the outer reaches of the heliosphere. As they travel away from the Sun, their instruments detect changes in particle populations, magnetic fields, and radiation levels. These measurements reveal where the solar wind slows, where energetic particles from the Sun diminish, and where particles from interstellar space become more prominent. The boundary is not a line drawn in darkness. It is a region of changing conditions, subtle in appearance but physically real. One important part of this outer domain is the termination shock. A shock in physics is a sudden change in pressure, density, and speed within a flowing medium. The solar wind moves faster than the speed at which pressure disturbances travel through that plasma, meaning the charged gas. When the outward flow eventually meets enough resistance from the surrounding interstellar medium, it slows abruptly. This creates the termination shock. Beyond that point, the solar wind continues. But it is slower, hotter in the plasma sense, and more turbulent. The existence of this shock shows that the heliosphere is not just a gradual fading of solar influence. It has internal structure shaped by the mechanics of flowing plasma. Beyond the termination shock lies the heliosheath. This is the outer layer of the heliosphere where the slowed solar wind becomes compressed and disturbed as it continues to press against interstellar space. The heliosheath is not smooth. It contains changing magnetic conditions, waves, and complex particle behavior. It is a place where solar material still dominates, yet only with difficulty. The solar wind has spent much of its outward force, and the surrounding medium increasingly pushes back. Spacecraft data indicate that the heliosheath differs in thickness and character depending on direction. This asymmetry likely reflects the influence of the interstellar magnetic field, the incoming flow of interstellar gas, and the changing strength of the solar wind over the solar cycle. The heliosphere also acts as a shield, though not a perfect one. It affects the entry of cosmic rays, high-energy particles that come from beyond the solar system. Cosmic rays arise from energetic processes such as supernova remnants and perhaps other powerful galactic sources. As they approach the solar system, the magnetic structure carried by the solar wind helps reduce the number and energy of some of these particles reaching the inner regions. The shielding varies with solar activity. During times of stronger solar magnetic influence, more cosmic rays are deflected or slowed. During quieter solar periods, more can enter. This protective role makes the heliosphere an important part of the solar system's wider environment, even though it is invisible to ordinary sight. Neutral atoms from interstellar space can also enter the heliosphere in ways that charged particles cannot. Because they carry no electric charge, they are less controlled by magnetic fields. Some pass inward across the outer boundary and later become ionized, after which they join the complex plasma behavior inside the heliosphere. This exchange means the heliosphere is not a sealed container. It is a permeable region where the sun's influence dominates but does not isolate itself completely from the galaxy beyond. Matter and energy continue to interact across its boundary layers. Above and below the solar system, the heliosphere does not form a neat top and bottom like a roof and floor. Its shape is determined by pressure balance, solar output, and the direction of motion through interstellar space. It is often compared to a comet-like form or an extended bubble with a symmetry, but the exact shape remains under study. Observations indicate that it is rounded in some respects and compressed in others. It remains uncertain how long any trailing region extends and how strongly the interstellar magnetic field sculpts its form. What is known is that the heliosphere has a front-like direction facing the incoming interstellar flow and a broader outer structure that changes with conditions. This region marks the true outward reach of the Sun as an active star. Gravity extends farther in one sense, since distant icy bodies remain bound to the Sun at even greater distances. But the heliosphere defines something different. It marks the distance to which the Sun fills space with its own wind and magnetic influence before the surrounding galaxy begins to press back in a stronger way. It is the first major environmental edge of the solar system, not made of rock, ice, or orbiting bodies, but of flowing plasma meeting the thin matter between the stars. In that quiet encounter, the Sun's domain becomes visible through measurement, and the outer boundary of the solar system takes on a real physical shape. Beyond the broad outer layer of the heliosphere lies the boundary where the influence of the solar wind gives way to the surrounding interstellar medium in a more final sense. This boundary is called the heliopause. It is not a wall, not a bright frontier, and not a hard surface that can be touched. It is a transition where the outward pressure of the Sun's charged particles is no longer able to push farther against the material between the stars. Inside this boundary, the plasma is dominated by the solar wind. Outside it, the plasma belongs mainly to interstellar space. The heliopause therefore marks the practical end of the Sun's particle bubble and the beginning of a different physical regime, one shaped more directly by the galaxy beyond. The heliopause can be understood as a contact boundary between two large flows. On one side is the solar wind, weakened after its long outward journey and altered by its passage through the heliosheath. On the other side is the local interstellar medium, the thin gas and magnetic field through which the solar system moves. At the heliopause, these two domains meet but do not mix freely in a simple way. Their pressures balance in a shifting arrangement. The exact location changes with solar conditions and with the surrounding interstellar pressure. This makes the heliopause a living boundary in physical terms, not a fixed shell placed permanently at one distance. Evidence for the heliopause comes most directly from the Voyager spacecraft. As Voyager 1 and Voyager 2 travel outward, their instruments register changes in particle intensity, plasma conditions, and magnetic behavior. These changes indicate when the spacecraft leave the region dominated by solar particles and enter one where interstellar particles become much more important. The transition is subtle in some ways and sharp in others. Solar wind particles decline strongly. Galactic cosmic rays increase. Plasma density measured beyond the boundary rises to values more consistent with the local interstellar medium. These observations provide the strongest direct indication that the spacecraft have crossed from the Sun's outer bubble into interstellar space. This crossing does not mean the Sun's gravity ends there. The Sun's gravitational reach extends much farther. Distant icy bodies remain bound to it well beyond the heliopause. The importance of the heliopause lies elsewhere. It marks the end of solar dominance in the flow of plasma and magnetic structure. That is why it is such an important boundary in understanding what actually surrounds the solar system. The heliopause shows that the solar system exists within the galaxy, not only as a set of orbits, but also as a moving plasma environment with a real exterior edge. Outside the heliopause, space is still not empty in the absolute sense. It contains the interstellar gas of the local cloud, along with magnetic fields and energetic particles moving through the wider galactic environment, the plasma there is extremely thin, but it is denser than the solar wind in the outer heliosphere. This difference matters because even a small rise in particle density becomes significant in such rarefied conditions. The boundary itself is therefore defined by physical contrasts that can be measured even though they would remain invisible to ordinary sight. One region carries the sun's outward stream. The other belongs to the thin but persistent medium between stars. Magnetic fields near the heliopause are especially important and also somewhat complex. The sun carries its own magnetic field outward through the solar wind. The local interstellar medium has its own magnetic field as well. At the boundary, these fields interact, bend, and press against one another. Observations suggest that the field directions inside and just outside the heliopause are not always dramatically different in simple geometric terms, which at first made interpretation of Voyager data more difficult. Over time, however, the combination of particle data, plasma behavior, and field measurements made the crossing clearer. It remains an area of active study because the detailed structure of the boundary and the processes that operate there are not fully resolved. One process of interest near the heliopause is charge exchange. This occurs when a charged particle takes an electron from a neutral atom. In the outer solar system, such interactions can alter particle energies and create populations of energetic neutral atoms that travel long distances unaffected by magnetic fields. Missions that detect these neutral atoms can help map the outer heliosphere indirectly. In this way, the boundary of the Sun's domain is studied not only by direct travel, but also by remote sensing of particles produced through subtle atomic encounters. The heliopause is therefore not a still dividing line. It is a place where solar and interstellar matter influence one another continuously. It remains uncertain whether a true bow shock exists ahead of the heliosphere in the direction of the solar system's motion through the local interstellar medium. A bow shock would be similar in principle to the wave that forms in front of a boat moving through water or the compressed air in front of an object moving faster than the speed of sound. Earlier models often expected a clear bow shock beyond the heliopause. More recent observations suggest that the relative motion and local conditions may instead produce a gentler bow wave or compression region, rather than a strong shock. The matter is not settled in every detail, but current evidence indicates that the surrounding interstellar flow may be more moderate than once assumed. Above and below the solar system, the heliopause has no flat upper and lower faces. Its three-dimensional form depends on the direction of interstellar flow, the pressure of the local medium, the solar cycle, and the surrounding magnetic field. In some directions it may lie closer to the Sun. In others it may extend farther outward. It is shaped less like a geometric shell and more like a flexible outer skin around a moving, breathing plasma bubble. This is one reason the idea of simple cosmic layers above and below the solar system does not hold. Boundaries in space are usually created by forces, flows, and gradients rather than by rigid surfaces. Just beyond the heliopause, the solar system enters interstellar space in the most literal environmental sense available to present observation. There, the Sun is still the dominant light source for its planets, and small bodies far inward. But the surrounding plasma no longer comes from the Sun. The galaxy is now the immediate environment. This is a quiet but important shift. A spacecraft passing beyond the heliopause does not arrive at a dramatic scene. It enters a region that remains dark, sparse and cold, yet physically distinct from the space inside the heliosphere. The difference lies in origin, pressure, and particle population. The heliopause therefore stands as the meeting line of two realms. Within it, the Sun fills space with its own wind. Beyond it, interstellar matter resumes control. It is one of the clearest answers to what lies outside the solar system at its outer edge. There is no hidden chamber there, no abrupt drop, and no upper or lower shelf beyond the planets. There is only the thin local medium of the Milky Way, pressing softly but steadily against the fading breath of the Sun. At that edge, the solar system ceases to be a self-contained bubble of plasma and becomes once more part of the broader galactic sea through which it moves. Beyond the heliopause, the solar system is no longer enclosed by the Sun's outward wind, yet the Sun's gravity still extends far into space. In that broader gravitational domain, far beyond Neptune, there exists a population of icy bodies moving on distant paths. Among them is a region known as the scattered disk. This is not a dense belt and not a uniform shell. It is a sparse, extended population of objects whose orbits are long, stretched, and often tilted relative to the flatter plane followed by the major planets. The scattered disk belongs to the far outer solar system, a realm where sunlight is weak, motion is slow, and the history of planetary migration remains written into the paths of ancient frozen worlds. A disk in astronomy does not always mean a smooth, solid form. Here it refers to a broad distribution of bodies occupying a flattened but extended region around the Sun. The scattered disk differs from the more orderly regions inward of it because its objects do not move on nearly circular, stable paths close to the plane of the planets. Instead, many travel on eccentric orbits, meaning their paths are elongated rather than round. Some also have significant inclination, meaning their orbits are tilted relative to the main plane of the solar system. These features give the region its scattered character. The objects are not placed randomly, but their orbits show the marks of past gravitational disturbance, especially from Neptune. The scattered disk contains icy bodies left from the era of solar system formation. These are remnants of the outer protoplanetary disk, the broad rotating disk of gas and dust from which the planets formed. In the cold outer reaches, water ice, methane ice, nitrogen ice, and other frozen substances could survive. Small bodies there accumulated from collisions and gradual sticking among particles and larger fragments. Some became moons around the giant planets. Some remained independent. As the giant planets shifted from their original positions during the early history of the solar system, their gravity disturbed many of these small icy bodies. Neptune, as the outermost giant planet, played a particularly important role. Its repeated gravitational encounters altered the paths of many objects, sending some inward, ejecting some outward, and leaving others on the stretched orbits now associated with the scattered disk. This region is therefore not best understood as a place of ongoing chaos, but as a record of earlier dynamical shaping. Dynamical means shaped by motion and gravity through time. The orbits seen today preserve evidence that the outer planets did not remain perfectly fixed during the solar system's youth. Models supported by many observations indicate that the giant planets migrated, meaning their orbital distances changed through interactions with countless smaller bodies. In that process, Neptune moved outward and scattered nearby icy objects onto wider and more eccentric paths. The scattered disk keeps the result of that history in a frozen, slow-moving form. It is like a faint archive written not on paper or rock, but in orbital geometry. The objects in the scattered disk are often called trans-Neptunian objects because they orbit beyond Neptune. Some are large enough to be roughly spherical under their own gravity, while many are much smaller and irregular in shape. Their surfaces are dark, cold, and altered by radiation over immense spans of time. At such distances, sunlight is faint and temperatures are extremely low. Ices remain stable, though some surface materials may slowly change under exposure to energetic particles and weak but persistent solar radiation. Because these bodies are small and distant, they are difficult to observe. Even the larger known objects appear dim, and much of what is known comes from painstaking telescopic surveys and orbital calculations rather than from direct imaging of surface detail. One well-known scattered disk object is Eris, a dwarf planet whose discovery helped prompt the modern clarification of the term planet. Eris follows a distant, elongated orbit and is comparable in size to Pluto, though somewhat smaller in diameter according to current measurements. Its existence made clear that Pluto was not alone as an unusual outer body. The far solar system contains several large icy worlds that do not fit comfortably into the older simple picture of 9 planets, followed by empty space. Eris and similar bodies show that beyond Neptune, there exists a more complex population of frozen objects, ranging from relatively stable members of the Kuiper belt to more widely displaced members of the scattered disk. The scattered disk does not have a sharp outer edge known with certainty. Some objects on long paths extend to hundreds of astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, used as a standard measure within the solar system. At such ranges, one orbit can take many thousands of years. Because the objects are so faint and because surveys are incomplete, the full size and population of the scattered disk remain uncertain. Observations indicate that many bodies in this region have yet to be found. The known sample is therefore only a partial view of a much larger distant population. The region is also linked to other outer populations. Some bodies from the scattered disk may become short-period comets after further gravitational interactions guide them inward. A short-period comet is one that returns to the inner solar system on timescales of less than 200 years, often under the influence of the giant planets. In this sense, the scattered disk is not entirely isolated. It can serve as a reservoir from which some icy objects are gradually transferred inward. Yet within the region itself, the prevailing impression is stillness rather than traffic. The bodies are widely separated, each following its own slow arc around the Sun through a region of profound darkness. Above and below the solar system, as defined by the planetary plane, the scattered disk extends in a more vertically spread way than the classical arrangement of the major planets. Its objects can be found on tilted orbits, which means the far outer solar system is not a flat sheet. It grows thicker and less orderly with distance in this region. Even so, it is not a spherical cloud. It remains a broadly disk-related population, shaped by the same original rotating system from which the planets emerged. What changes is the degree of order. The farther reaches preserve less of the calm circular arrangement seen inward, and more of the gravitational roughness left by ancient planetary motion. This makes the scattered disk an important answer to what lies beyond the neat map of the planets. Beyond the major planetary orbits, the solar system does not end abruptly. It opens into a sparse outer population of icy remnants on stretched and inclined paths. These bodies are real members of the solar system bound to the Sun, but they inhabit a region where the old simplicity of textbook diagrams no longer applies. The Sun still governs them through gravity. Yet they move in ways that show how deeply Neptune and the early giant planets have shaped the outskirts. In the scattered disk, the far edge of the solar system appears not as a clean boundary, but as a quiet field of distant survivors left on wandering, frozen roads. Beyond Neptune, and inward from the more stretched paths of the scattered disk, there lies a broader and more orderly outer region known as the Kuiper belt. This is a wide population of icy bodies orbiting the Sun at great distance, mostly beyond Neptune's path, and mostly within a flatter and less disturbed arrangement than the scattered disk. It is often compared in a general way to the asteroid belt, but the comparison is limited. The Kuiper belt is much larger in scale, much colder in temperature, and made chiefly of frozen materials rather than mainly rocky and metallic ones. It is not packed densely with bodies. It is spacious and sparse, yet it contains a great many objects, from small fragments to dwarf planets, and together they preserve a record of how the outer solar system forms and settles. The Kuiper belt consists of remnants from the early solar system, bodies that never combine into a full-size planet. In the cold outer disk around the young Sun, ices could survive far more easily than in the warmer inner regions. Water ice remains common there, along with other frozen substances such as methane, carbon monoxide, carbon dioxide, and nitrogen in varying mixtures depending on temperature, size, and surface history. These materials collect into small worlds during the solar system's earlier stages. Some grow large enough for gravity to pull them into roughly spherical shapes. Many remain irregular. Over time, collisions break some apart, and radiation alters exposed surfaces. Even after billions of years, the belt remains a population of leftovers rather than a finished planetary layer. The term belt can suggest a narrow ring, but the Kuiper belt is better understood as a broad zone. Many of its best-known members orbit between about 30 and 50 astronomical units from the Sun, though exact classification depends on orbital behavior and on how the different outer populations are defined. An astronomical unit is the average distance between Earth and the Sun, and in the Kuiper belt those units accumulate into immense ranges at such distances. The Sun still dominates by gravity, but its light is weak and the orbital periods are very long. A body in this region may take hundreds of years to complete one revolution around the Sun. Time moves differently there, not in its basic physics, but in the pace at which orbital change becomes visible. Not all Kuiper belt objects move in the same way. Some belong to what is often called the classical Kuiper belt, where orbits are relatively moderate in eccentricity and inclination. Eccentricity describes how stretched an orbit is. Inclination describes how tilted it is relative to the plane of the major planets. Within the classical population, some objects follow especially calm paths and are sometimes described as cold classical objects. Here the word cold refers not mainly to temperature, but to the gentleness of their orbital distribution. These objects tend to have lower inclinations and are thought to preserve conditions close to their place of origin. Other bodies have somewhat more excited orbits, meaning more tilt and stretch, suggesting a more disturbed past. A large part of the Kuiper belt is also shaped by orbital resonance with Neptune. A resonance is a repeating gravitational relationship in which orbital periods form simple numerical ratios. Pluto is the best-known example. It completes 2 orbits around the Sun in the time Neptune completes 3. This 3-to-2 relationship prevents the two bodies from coming dangerously close, despite the crossing of their projected orbital paths. Pluto therefore belongs to a resonant population rather than to the classical belt. Many other resonant objects exist as well, held in long-term orbital patterns that reflect Neptune's influence. These resonances are not signs of chance. They point to the history of outward planetary migration and the gradual capture of small bodies into stable repeating arrangements. Pluto remains one of the most studied Kuiper belt worlds. Though now classified as a dwarf planet rather than a major planet, it serves as an important representative of this region. It has a complex surface of nitrogen ice, methane ice, and water ice bedrock. along with a thin atmosphere that changes as it moves along its elongated orbit. Observations from spacecraft and telescopes show plains, mountains of water ice, and signs of active surface renewal. Pluto demonstrates that bodies in the Kuiper Belt are not necessarily simple frozen stones. Some are geologically varied, internally layered, and surprisingly dynamic despite the great cold and weak sunlight of their environment. Other large Kuiper Belt objects include Haumea and Makemake, along with many smaller bodies that continue to be discovered. Haumea is unusual for its elongated shape and rapid rotation, and it appears associated with a family of fragments likely produced by a past collision. Makemake shows a bright, icy surface and belongs to the larger class of dwarf planet candidates or confirmed dwarf planets beyond Neptune. These examples show that the belt is not a uniform collection. Its members differ in size, color, reflectivity, composition, and dynamical behavior. Some surfaces are darkened by radiation-processed material. Others remain brighter, perhaps because of fresh ice exposure or volatile transport. Each object offers a variation on the same broad theme of cold outer survival. The Kuiper Belt is important because it preserves material from the era of planet formation in a relatively undisturbed state, especially among its calmer populations. In the inner solar system, collisions, solar heating, geological activity, and planetary growth erase much of the earliest record. In the Kuiper Belt, many bodies remain small and cold enough to preserve older compositions and structures. They're not entirely unchanged, but they are less transformed than the larger planets. By studying them, astronomers learn about the original outer disk of the solar system, the migration of Neptune, and the distribution of ices and organics in the young planetary system. Organics in this context are carbon-based compounds, not living material, but chemical ingredients that matter for planetary chemistry. Above and below the solar system, the Kuiper Belt remains broader than the main planetary plane but flatter than a true cloud. It has thickness because many objects have inclined orbits, yet it still reflects the original disk-like form of the early solar system. The central impression is not of a sphere surrounding the Sun equally in all directions. It is of a distant, flattened population beyond Neptune, extending around the Sun in a broad outer band. What lies above and below this region is mostly more empty space, with fewer Kuiper Belt objects as one moves farther from the central plane of the system. The Kuiper Belt therefore answers an important part of what is actually out there beyond the planets. It is not a blank outer darkness. It is a real and extensive population of icy remnants, occupying a cold broad zone where Neptune's influence is still felt and early solar system history remains visible in orbital structure and frozen surfaces. It is quiet, sparse, and dim, yet scientifically rich. In this region, the solar system shows itself not as a clean sequence ending with the last giant planet, but as a layered system with a wide outer plane of ancient icy bodies still circling the Sun in deep and patient cold. Neptune stands as the outermost major planet of the solar system, a large world of deep blue colour orbiting far beyond Saturn, Jupiter, and Uranus. At this distance, sunlight has weakened to a pale fraction of its strength at Earth, and the Sun itself appears much smaller in the sky. Yet Neptune is not a quiet or inactive sphere resting in remote darkness. It is a dynamic planet with a layered atmosphere, fast winds, a complex magnetic field, faint rings, and a system of moons that extends its influence through the cold outer planetary region. In moving inward from the Kuiper Belt, Neptune marks the first great arrival at a major planetary body, one large enough to reshape surrounding space by gravity, and one important enough to define the outer architecture of the solar system. Neptune is classified as an ice giant. This term does not mean that the planet is made mainly of ordinary surface ice like a frozen sea or glacier in planetary science. The word ice refers to volatile substances, materials that condense at low temperatures, such as water, ammonia, and methane. Ice giants differ from gas giants like Jupiter and Saturn because they contain a larger proportion of these heavier volatile materials and a smaller proportion of hydrogen and helium in their deep interiors. Neptune still has a thick atmosphere rich in hydrogen and helium, but much of its mass is thought to lie in a deep mantle-like region composed of hot, dense, fluid mixtures of water, ammonia, and methane above a rocky core. These interior layers are not directly visible, yet they help explain the planet's mass, density, magnetic field, and internal heat. The blue colour of Neptune comes largely from methane in its atmosphere, which absorbs red wavelengths of sunlight and leaves more blue light to be scattered and reflected. The exact richness of Neptune's colour may also involve other atmospheric processes that are not yet fully understood. Observations indicate that methane alone does not explain every detail of the planet's appearance. What is clear is that the visible atmosphere is not a still blue shell. It contains bands, clouds, storms, and hazes that shift over time. High-altitude clouds made of methane ice can form and drift across the upper atmosphere, while deeper layers remain hidden beneath the visible cloud tops. One of Neptune's most striking traits is the speed of its winds. Despite the weak sunlight at that distance, the planet hosts some of the fastest winds measured in the solar system. These winds can move at speeds of more than 1,000 kilometers per hour. The reason lies not in solar heating alone, but in the planet's own internal energy. Neptune radiates more energy into space than it receives from the Sun, which means internal heat rises through the planet and helps drive atmospheric motion. The exact details of how this internal heat powers such strong winds remain an area of study, but the broad pattern is well established. Neptune is not merely a frozen outer sphere lit faintly from afar. It is an active world with weather sustained in part from within. The planet's atmosphere is made chiefly of hydrogen and helium, with methane present in smaller amounts. As pressure increases with depth, conditions become more extreme. The upper atmosphere gives way to thicker, denser layers below. Beneath those layers, models indicate a vast interior region of hot compressed fluid. Temperature and pressure rise steadily inward, so the materials there behave in ways unlike ordinary liquids or ices on Earth. In this deep environment, water, ammonia, and methane exist under enormous compression. Their behavior contributes to the structure of the planet and likely to the unusual nature of its magnetic field. Neptune's magnetic field is remarkable because it is both tilted and offset relative to the planet's center. Unlike the simpler dipole-like field often imagined around a planet, Neptune's field appears generated in a more complicated geometry. This likely reflects the way electrically conducting fluids move within the planet's deep interior. The magnetic field interacts with the solar wind, creating a magnetosphere, a region of space where charged particles are influenced strongly by planetary magnetism. Even at Neptune's great distance from the Sun, this interaction remains important. The solar wind is thinner there than near Earth, but Neptune's magnetic environment still shapes surrounding charged particles and defines part of the planet's local spatial domain. Neptune also has a faint ring system. These rings are much less bright and massive than the famous rings of Saturn, but they are real and scientifically important. They consist of dark particles and dust arranged in several narrow structures around the planet. Some portions appear denser than others, forming arc-like concentrations rather than perfectly even rings. The reasons for this pattern involve gravitational effects and the influence of nearby moons. The rings are delicate and dim, requiring careful observation to detect. Yet they remind the mind that Neptune is not an isolated sphere. It is the centre of a planetary system with matter in orbit around it at many scales. Among Neptune's moons, Triton is by far the most significant. Triton is large, cold, and unusual because it moves around Neptune in a retrograde orbit, meaning it travels in the opposite direction from the planet's rotation. This strongly suggests that Triton does not form alongside Neptune in the usual way. Instead, it is thought to be a captured object, likely once an independent body from the outer solar system, perhaps related to the Kuiper Belt population. Triton has a surface of nitrogen ice, water ice, and other frozen materials, along with evidence of past and perhaps ongoing internal activity. Spacecraft observations reveal a young-looking surface in many areas and dark streaks likely formed by material venting from below. Triton stands as one of the most compelling worlds in the outer solar system, but within Neptune's domain it is best understood first as a sign of the planet's strong gravitational reach and complicated history. Neptune's role in the architecture of the solar system extends far beyond its visible body. Its gravity helps shape the structure of the Kuiper Belt and the scattered disk. Resonant objects beyond Neptune move in repeated orbital relationships with it, and scattered objects bear the marks of earlier close encounters and long-term gravitational influence. Neptune therefore acts as a boundary keeper between the major planets and the distant icy populations beyond. Its own orbit traces the outer edge of the classical planetary sequence, while its gravitational effects continue outward into regions already described. Above and below the solar system's main planetary plane, Neptune's own system spreads only modestly compared with the full outer solar system, yet it still adds thickness and structure to the region. Its tilted magnetic field, ring system, and varied moons create a local environment around the planet rather than a simple empty zone. What appears from afar as one blue point in darkness is in fact a complex planetary realm. It is cold, dimly lit, and remote, but not simple. Neptune thus represents the outer major planetary domain in full form. It is an ice giant with strong winds, internal heat, a strange magnetic field, faint rings, and a powerful influence on surrounding bodies. In moving inward from the distant icy populations, the solar system becomes more concentrated here. Gravity gathers matter into planet, moon, and ring. The blue world stands in weak sunlight at the edge of the major planets, holding its own atmospheric motion and extending its authority outward through resonance and capture. In Neptune's remote domain, the outer solar system becomes planetary again. Uranus lies inward from Neptune, still deep in the outer planetary region, still far beyond the warmth of the inner solar system, but distinct in character and appearance. In visible light it presents a pale blue-green disk, quieter in outward appearance than Neptune, with softer atmospheric contrast and a more subdued visual texture. Yet this calm impression does not mean simplicity. Uranus is a large and unusual world, another ice giant, with a deep layered interior, a cold upper atmosphere, a faint ring system, many moons, and one of the most striking rotational tilts in the solar system. In the steady inward path from the outermost regions toward the Sun, Uranus marks a quieter giant domain where unusual geometry shapes everything from seasons to magnetism. Like Neptune, Uranus is called an ice giant because a large portion of its mass is thought to consist of heavy volatile materials such as water, ammonia, and methane under conditions of great pressure and temperature beneath a hydrogen and helium atmosphere. The word ice here does not describe the visible surface, because Uranus has no solid surface on which a traveller could stand. The visible disk is the upper atmosphere, a high and cold layer above deeper regions of compressed fluid. Beneath the cloud tops, pressure rises continuously, and the atmosphere merges into denser internal layers rather than ending at a clear boundary. This gradual deepening is a common feature of the giant planets. They are not made of separate stacked shells in the ordinary sense, but of broad regions that blend into one another as conditions change. The colour of Uranus comes mainly from methane in the upper atmosphere. Methane absorbs red light and leaves more blue and green light to be reflected and scattered back into space. In this respect, Uranus resembles Neptune, though its tone is generally paler. The visible atmosphere often appears less dramatic than Neptune's, especially in smaller telescopic views. But careful observations show that Uranus is not without weather. Clouds, hazes, and storms do occur. Some are seasonal. Some are short-lived, and some become clearer when the viewing geometry changes over time. The subdued appearance of Uranus reflects both its atmospheric properties and the limitations of distant observation. Beneath that pale stillness there is real motion. One of the defining features of Uranus is its extreme axial tilt. The planet rotates with its axis tipped by about 98 degrees relative to its orbit around the Sun. This means Uranus effectively rolls along its orbital path with one pole and then the other facing the Sun over long spans of time. Most planets spin more upright relative to their orbital plane, even if tilted by some amount. Uranus is different enough to make its system feel almost sideways. This unusual orientation gives rise to extreme seasons. Because Uranus takes about 84 Earth years to orbit the Sun, each season lasts for decades. During parts of its year, one hemisphere receives prolonged sunlight while the other spends a long interval in darkness. Later, the arrangement reverses. This long seasonal pattern affects the atmosphere in complex ways. Changes in sunlight alter temperature structure, cloud formation, and circulation over time, though the full response is difficult to study because human observation covers only a limited fraction of one Uranian year. Observations indicate that the atmosphere becomes more active near equinox, when the Sun shines more evenly across the planet. But the exact balance between solar heating and internal heat remains a subject of study. Uranus emits relatively little excess internal heat compared with Neptune, which is one reason its atmosphere may appear more subdued on average. It remains uncertain why Uranus seems to radiate less internal energy than Neptune despite their broad similarities in size and composition. One possibility is that an ancient event affects how heat moves outward from its interior, but the details are not settled. The origin of Uranus's great tilt also remains uncertain. The leading broad idea is that a large impact or a series of major collisions early in solar system history alters its orientation. Such events are plausible during the era of planet formation, when large bodies frequently collide and rearrange one another. Observations strongly support the fact of the tilt itself, but they do not preserve a direct record of the exact event that causes it. What remains visible today is the consequence. Uranus rotates in an unusual way, and its rings and many of its moons orbit in the same tilted plane, showing that the whole local system shares this altered geometry. Uranus has a magnetic field that is both tilted and offset from the planet's centre, much like Neptune's in its general strangeness, though with its own details. This suggests that the field is generated in a region that is not arranged like the deeper metallic hydrogen layers thought to operate in Jupiter and Saturn. Instead, electrically conducting fluids in the intermediate interior may play a greater role. The result is a magnetosphere with a lopsided and changing relationship to the solar wind. As Uranus rotates, the orientation of its magnetic field relative to the incoming solar wind changes in an especially complex way because the planet itself is tipped so dramatically. This produces a magnetic environment unlike that of any other major planet. The ring system of Uranus is faint and dark. It lacks the broad brightness of Saturn's rings, and instead consists of narrow bands made of relatively dark particles. These rings are not especially massive, but they are important in showing that Uranus, like the other giant planets, has a structured orbital environment close to the planet. Their darkness suggests material that does not reflect much sunlight, possibly altered by radiation over time. Shepherding effects from small moons may help maintain some ring structure. Though the detailed dynamics vary from ring to ring, the rings remain delicate and dim, easier to appreciate scientifically than visually, but they contribute to the quiet architecture of the Uranian system. Uranus also possesses a large family of moons. The major moons, including Titania, Oberon, Umbriel, Ariel, and Miranda, are worlds of ice and rock shaped by internal history, impacts, and orbital evolution. Miranda is especially notable for its strange surface, with cliffs, ridges, and mixed terrains that suggest a complex past involving disruption or internal activity. These moons do not form a simple collection of frozen stones. Each has a distinct surface history written in craters, fractures, and ancient geological change. Still, within the present section, their importance lies mainly in showing that Uranus rules a complete planetary system around itself, with orbiting bodies that reflect its tilted plane and distant gravitational order. Above and below the main plane of the solar system, Uranus contributes to the broad thickening already present in the outer regions, yet its own local definition of up and down is transformed by its sideways orientation. Relative to its orbit, its poles point in directions unlike those of the other planets. Relative to its moons and rings, however, the system remains coherent. This is a reminder that orientation in space is always relative. Uranus does not violate order. It simply carries a different order, one established by its axis, its rotation, and the history that places it in this state. Uranus therefore stands as a calm but deeply unusual giant. It is pale, cold, and distant, with soft atmospheric features, faint rings, numerous moons, weak outward heat compared with Neptune, and a rotation so tilted that its seasons unfold in long and singular patterns. In moving inward through the solar system, the outer planetary realm grows richer in detail without becoming louder in appearance. Uranus keeps much of its complexity beneath a quiet face. It occupies a region where the sunlight is dim, the years are long, and the geometry of a planet can differ profoundly from the familiar arrangement nearer the Sun. Saturn lies inward from Uranus, and with it the solar system takes on a different visual richness. The pale stillness of the ice giants gives way to a vast gas giant surrounded by an extensive ring system that catches light with unusual clarity. Saturn is not the largest planet, but it is the most visibly elaborate. Its rings spread outward in wide, thin bands. Its atmosphere is layered in soft belts and zones, and its many moons create a surrounding realm of ice, rock, haze, and orbital resonance. In the steady inward movement through the solar system, Saturn marks a region where the broad architecture of planet, ring, and moon becomes especially clear. Saturn is a gas giant, meaning most of its mass is made of hydrogen and helium rather than the larger fraction of water, ammonia, and methane-rich material thought to dominate the deeper interiors of Uranus and Neptune. Even so, Saturn is not a simple ball of gas. Like all giant planets, it has a layered internal structure. The visible atmosphere forms only the outer skin of a much deeper world. Beneath the clouds, pressure and temperature rise steadily. Hydrogen changes its behavior under compression, and deeper still it is thought to become metallic hydrogen, a form in which hydrogen conducts electricity under extreme pressure. Below that region there is likely a core containing heavier elements, though its exact size and structure remain areas of active study. Observations indicate a complex interior shaped by gravity, heat flow, and rotation, but it remains uncertain how sharply divided its deepest layers are. The atmosphere of Saturn is made chiefly of hydrogen, with helium and smaller amounts of methane, ammonia, water vapor, and other compounds. In visible light, the planet appears muted gold or pale yellow, with cloud bands that are less strongly contrasted than those of Jupiter. This softer appearance results partly from high-altitude hazes that blur the boundaries between atmospheric zones. Even so, Saturn's atmosphere is active. It contains strong winds, long-lasting circulation patterns, storms, and seasonal changes. Some storms can become very large, including rare planet-encircling disturbances known as great white spots. These appear at long intervals and reveal that Saturn's apparently gentle face conceals large-scale atmospheric energy. Like Jupiter, Saturn rotates rapidly. This quick rotation affects the planet's shape, making it noticeably flattened at the poles and broader at the equator. The rotation also helps organize the atmosphere into bands where east-west winds dominate. Wind speeds can become very high, especially near the equator. Beneath the visible clouds, deeper circulation likely continues in ways that are still being studied through gravity data and atmospheric modeling. The upper atmosphere alone does not tell the full story. Saturn's weather, structure, and heat flow are linked to processes extending far below what telescopes can see. Saturn emits more energy than it receives from the Sun, which means it has a significant internal heat source. This excess energy likely arises from leftover heat from formation, slow gravitational contraction, and perhaps from the separation of helium from hydrogen deep inside the planet. In one leading idea, droplets of helium form and sink through the liquid hydrogen-rich interior, releasing gravitational energy as heat. This process is sometimes called helium rain. Though it is unlike rain in any ordinary earthly sense, it refers to phase separation under enormous pressure. Such internal processes help explain why Saturn remains active despite its great distance from the Sun and the weakness of sunlight in its outer domain. The most distinctive feature of Saturn is its ring system. These rings are extremely broad yet remarkably thin compared with their width. They are made chiefly of countless particles of water ice, ranging in size from tiny grains to larger chunks. Mixed with the ice is a smaller amount of darker material. From a distance, the rings seem like smooth, continuous bands, but close study shows that they are composed of innumerable orbiting pieces, each following Saturn's gravity, gaps, waves, braids, and narrow ringlets appear throughout the system, shaped by gravitational interactions with moons and by collisions among the ring particles themselves. The rings are not a rigid structure. They are a dynamic disk of orbiting debris in constant subtle motion. The brightness of Saturn's rings comes largely from the reflectivity of water ice. This makes them far more luminous than the darker rings of Uranus and Neptune, yet their beauty should not hide their complexity. Some ring features are maintained by shepherd moons, small moons whose gravity helps confine ring particles into narrow bands. Other structures arise from orbital resonances, where repeated gravitational tugs from moons influence the motion of ring material. These repeated interactions can create gaps and patterns that remain stable over long times. The rings, therefore, are not only decorative, they are a visible demonstration of orbital mechanics acting across a thin, brilliant disk. It remains uncertain exactly how old Saturn's rings are in their present form. Some evidence suggests that they may be relatively young on solar system timescales, perhaps formed from the breakup of an icy moon or comet-like body. Other evidence leaves room for more complex histories involving recycling of ring material over long periods. What is known is that the rings are not permanent in a simple sense. Ring particles collide, spread, darken, and gradually interact with Saturn's environment. The current ring system is therefore best understood as an evolving structure rather than an eternal feature. Saturn's moons form one of the richest planetary systems in the solar system. Titan is the largest and most remarkable among them. It is larger than the planet Mercury and holds a thick atmosphere made mostly of nitrogen, with methane playing a major role in its chemistry and weather. Titan has clouds, rain, rivers, lakes, and seas, though in its case these involve methane and ethane rather than water. Beneath its icy crust, observations indicate that a liquid water ocean may exist. Titan stands as a world of immense scientific interest because it combines complex organic chemistry with active surface and atmospheric processes. Enceladus, a smaller moon, is also notable because it vents water-rich plumes from its south polar region, indicating a subsurface ocean beneath an icy shell. These moons show that Saturn's system is not only a ringed planet but a collection of active worlds. Other moons, from large cratered bodies to small irregular satellites, add depth to Saturn's domain. Some sculpt the rings, some preserve ancient surfaces, some may be captured objects. Together they create a layered orbital environment extending well beyond the planet itself. Around Saturn, gravity orders matter into rings close in, major moons farther out, and distant irregular satellites beyond. This arrangement makes the region feel broad and structured rather than empty. Above and below the main planetary plane, Saturn's rings remain extremely flat, reinforcing the disk-like order of the solar system. Yet the moons add vertical spread through slight orbital tilts, and the planet's magnetic and particle environment extends beyond the visible rings. What first appears as a luminous flat ornament becomes, on closer thought, a full three-dimensional planetary realm. Saturn therefore occupies a middle region of the solar system where scale, motion, and structure become especially graceful. It is a gas giant with a deep atmosphere, strong winds, internal heat, an immense ring system of icy particles, and a family of moons that include some of the most intricate worlds known. In moving inward, the solar system here becomes both more familiar in brightness and more elaborate in design. Saturn gathers light softly, spreads it through rings, and holds around itself a wide system that turns quiet orbital order into visible form. Jupiter lies inward from Saturn and stands as the most massive planet in the solar system. Its presence changes the scale of everything around it. The planet is so large that all the other planets together still do not equal its mass. In the steady inward movement through the solar system, Jupiter marks a region where gravity becomes a dominant organizing force, not only for its own atmosphere and moons, but for the surrounding architecture of small bodies, resonances, and long-term orbital stability. It is a gas giant of immense depth and energy, wrapped in bands of cloud, marked by storms, surrounded by faint rings, and attended by a large family of moons. Around Jupiter, The solar system feels less like a sequence of separate objects and more like a system shaped by a powerful center of local order. Like Saturn, Jupiter is made mostly of hydrogen and helium. It has no solid surface that can be reached in the ordinary sense. The visible disk is the upper atmosphere, a region of cloud tops suspended above deeper layers where pressure and temperature rise continuously. As one moves inward through Jupiter's atmosphere, gases become denser and hotter until they merge into fluid states under enormous compression. At greater depths, hydrogen is thought to become metallic hydrogen, a state in which it conducts electricity. This deep conducting layer likely plays a major role in generating Jupiter's magnetic field. Beneath it, there is believed to be a core region enriched in heavier elements, though observations indicate that the core may not be sharply bounded in a simple way. It remains uncertain exactly how compact or diffuse the deepest central structure is. The visible atmosphere of Jupiter is arranged in alternating dark belts and lighter zones that circle the planet parallel to the equator. These bands are produced by strong east-west winds moving in opposite directions at different latitudes. The boundaries between them can remain stable for long periods, yet the finer details shift constantly. Clouds rise, spread, sink, and shear apart. Colors vary from white and cream to red, brown, and orange, depending on chemical composition, altitude, and the effects of sunlight and radiation on atmospheric compounds. Ammonia plays an important role in the upper clouds, while deeper cloud layers likely include ammonium hydrosulfide and water. What appears from afar as a striped planet is in reality a deep and changing fluid system. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a vast storm larger than Earth that has persisted for centuries. It is an anticyclonic storm, meaning a large rotating system of high pressure. The exact processes that allow it to endure for so long are still studied, but its longevity reflects the energy and depth of Jupiter's atmosphere, along with the absence of a solid surface that would otherwise weaken such circulation. The Great Red Spot has changed in size and shape over time, and observations indicate that it has been shrinking in its visible extent compared with the earlier centuries. Still, it remains one of the clearest signs that Jupiter's atmosphere is not a passive shell but a powerful moving environment. Jupiter emits more energy than it receives from the Sun. This means that internal heat contributes significantly to its atmospheric activity. Some of this heat is leftover energy from formation, and some arises from the slow contraction of the planet under its own gravity. As Jupiter gradually settles, gravitational energy is converted into heat. This internal source helps sustain convection, the upward and downward movement of material driven by heat and density differences. Convection, rotation, and composition together give rise to the complex circulation patterns visible across the planet. Jupiter's brightness in the night sky may seem calm, but beneath that brightness lies continuous motion on a scale larger than any weather system on Earth. The magnetic field of Jupiter is the strongest planetary magnetic field in the solar system. It creates a magnetosphere of enormous size, extending millions of kilometers into space and forming a huge region where charged particles are trapped and guided. This magnetosphere is so large that, if it were visible from Earth, it would appear bigger than the full moon in the sky by a wide margin. It interacts with the solar wind. But Jupiter's own rotation and internal magnetic power dominate the local environment. Radiation belts within this magnetosphere are intense, and charged particles move through them at high energies. Around Jupiter, space itself becomes part of the planet's system in a direct physical way. Jupiter also has a faint ring system, though it is much less prominent than Saturn's. These rings are made mainly of dust rather than bright icy particles. They are thought to be supplied by impacts on small inner moons, which release fine material into orbit. The rings are dim and delicate, important scientifically but not visually dominant. Their existence, however, reinforces an important point. Jupiter is not only a giant sphere, it is the center of a structured orbital domain with dust, moons, plasma, and magnetic interactions extending outward in many layers. The moon system of Jupiter is one of the most significant collections of worlds in the solar system. The four largest moons, Io, Europa, Ganymede, and Callisto, were first observed by Galileo and remain foundational objects in planetary science. Each is distinct. Io is the most volcanically active world known, its interior heated by tidal forces generated through the pull of Jupiter and orbital resonance with neighbouring moons. Europa has a bright icy crust beneath which observations strongly suggest a deep liquid water ocean. Ganymede is the largest moon in the solar system and has its own magnetic field, a rare property for a moon. Callisto, darker and more ancient in appearance, preserves a heavily cratered surface that records long spans of solar system history. These four moons alone make Jupiter's realm a system of worlds, rather than a single planet with minor companions. Tidal force is the stretching caused by gravity acting differently across an object's width. Around Jupiter, tidal effects are especially important. They heat interiors, maintain orbital resonances, and help shape geological activity on moons that would otherwise be much colder and quieter. This is one of the reasons Jupiter has such a strong organizing role. Its gravity not only holds moons in orbit, it changes their internal states and long-term evolution. Europa's hidden ocean, Io's volcanoes, and the resonant dance among the large moons all reflect Jupiter's commanding mass. Jupiter also influences regions far beyond its immediate moon system. It helps shape the asteroid belt through resonances that create gaps and through long-term perturbations that alter the orbits of smaller bodies. It affects the paths of comets entering the inner solar system and sometimes captures or redirects them. In early solar system history, Jupiter likely plays a major role in determining how material is distributed inward and outward. Its formation may even help limit the growth of a planet in the asteroid belt region by stirring that zone too strongly for easy accumulation. In this way, Jupiter is not simply one stop along the inward path. It is a structural force in the architecture of the whole planetary system. Above and below the main plane of the solar system, Jupiter's influence extends through inclined moons, vast magnetic regions, and long-term gravitational effects on small bodies. The planet itself remains aligned with the general disk-like order of the system, yet its local environment is fully three-dimensional. Radiation, plasma, dust, and orbiting worlds create depth around the giant rather than a flat arrangement alone. Jupiter therefore stands as the great gravitational organizer of the solar system's middle region. It is a gas giant with a deep atmosphere, powerful storms, strong internal heat, an immense magnetic field, faint rings, and a family of moons that are worlds in their own right. In moving inward, the solar system here becomes heavier in influence and more forceful in structure. Jupiter does not merely occupy space, it shapes the spaces around it, and through that shaping it gives order to much of what lies nearby. Inward from Jupiter, the solar system opens into the asteroid belt, a broad region populated by rocky and metallic bodies orbiting the Sun between the paths of Mars and Jupiter. In simple illustrations, this belt is often shown as a crowded band of tumbling stones pressed close together, but the true region is much more spacious. The asteroids are numerous, yet the distances between them are usually very large. a spacecraft can cross the belt without any serious chance of striking one by accident. The asteroid belt is therefore not a wall and not a field of constant collision. It is a dispersed population of remnants, a zone where early planetary building is interrupted and where much of the material from the young solar system remains preserved in smaller forms. These bodies are leftovers from the age of planet formation. In the early solar system, dust grains within the protoplanetary disk gradually stick together, forming larger clumps, then kilometre-scale bodies, then larger planetesimals. A planetesimal is a small early building block of a planet. In many regions, this process continues until full planets emerge. In the asteroid belt, however, the process does not run to completion. The gravitational influence of nearby Jupiter stirs the region strongly, increasing the speeds of collisions and making it more difficult for material to gather calmly into one large world. Instead of forming a planet, much of the matter remains divided among countless smaller bodies, with collisions breaking some apart and reshaping others across billions of years. The total mass of the asteroid belt is modest, far less than the mass of Earth, and even much less than the mass of the Moon. This reveals an important truth. The belt is not the broken remains of a large planet that once exists intact in that region. Observations and models indicate that no Earth-sized or even Moon-sized planet forms there and then shatters. Rather, the belt is a region where planetary growth remains incomplete. It preserves material that never fully assembles, later modified by impacts, heating in some cases, and long-term gravitational disturbance. The image of a destroyed planet is dramatic, but it does not fit the evidence. The quieter explanation is the more accurate one. The asteroid belt is a place where formation stalls. The asteroids themselves vary greatly in size. Many are small irregular objects only a few kilometers across or less. A few are much larger. Ceres is the largest object in the belt and is classified as a dwarf planet. It is large enough for gravity to pull it into a nearly spherical shape. Vesta, Pallas, and Hygeia are also among the major bodies. Ceres appears especially important because it preserves signs of internal differentiation, meaning that its material separates into layers to some degree, and because observations suggest that water-rich materials are present within it. Vesta, by contrast, is a more rocky and differentiated body with a crust, mantle, and large impact basins that reveal part of its interior. These larger asteroids show that the belt is not made only of simple rubble. Some members become complex enough to begin behaving like small worlds. Composition across the asteroid belt is not uniform. Broadly speaking, the inner part contains more stony, silicate-rich bodies, while farther outward the proportion of darker, carbon-rich material increases. Carbon-rich means rich in carbon-bearing compounds and often associated with primitive material little changed since early solar system history. Some asteroids are metallic, likely exposed fragments of once larger bodies whose interiors separate during early heating and later suffer major impacts. This compositional diversity matters because it preserves the temperature structure of the early solar system. Closer to the Sun, conditions favour rock and metal. Farther out, cooler conditions allow more volatile rich material to survive. The belt therefore serves as a boundary zone where different kinds of planetary matter remain side by side. Collisions play a central role in the belt's history. Over immense spans of time, asteroids strike one another, sometimes gently enough to alter surfaces and sometimes violently enough to shatter a parent body into whole families of fragments. An asteroid family is a group of objects that share similar orbital properties and likely originate from a common collision. By studying these families, astronomers reconstruct parts of the belt's history and estimate the ages of disruptive events. Some asteroids remain relatively intact. Others are rubble piles, loose collections of fragments held together mainly by gravity after reaccumulating from a past impact. This means that an asteroid is not always a single solid stone. It can be a fragile aggregate, shaped by repeated collisions and slow reassembly. The belt is also marked by resonances with Jupiter. A resonance is a repeating gravitational relationship based on simple orbital ratios. In the asteroid belt, certain distances from the Sun correspond to resonances where Jupiter's repeated pull destabilizes asteroid orbits over long times. These regions become depleted, creating gaps known as Kirkwood gaps. The gaps are not empty lines carved at once, but slowly cleared regions where orbits become unstable. Some asteroids are nudged inward or outward. Others acquire more elongated paths and may eventually cross the orbits of inner planets. In this way, Jupiter continues to shape the belt long after its initial formation. The asteroid belt is therefore not merely a leftover zone. It remains a gravitationally active region whose structure reflects ongoing orbital influence. Some material from the belt reaches Earth in the form of meteorites. When fragments are knocked from asteroids by collisions and later fall to Earth, they carry direct samples of ancient solar system matter. These meteorites reveal a wide range of histories. Some preserve primitive composition close to the early solar nebula, the original cloud of gas and dust from which the solar system forms. Others come from bodies that heat, melt, and separate internally. By studying them in laboratories, scientists learn about timing, chemistry, water content, and early heating processes that cannot be observed directly in the distant past. The asteroid belt, therefore, is not only an external region of space, it contributes physical evidence that arrives on Earth itself. Above and below the main plane of the solar system, the asteroid belt has some vertical thickness because asteroid orbits are not perfectly flat. Their inclinations vary, though the belt remains a disk-related structure rather than a spherical cloud. The overall impression is still one of a broad band around the Sun, but with countless individual paths crossing slightly above and below the central plane. This gives the region depth without making it chaotic. What lies above and below within the belt is more of the same dispersed orbital population, thinning gradually away from the main concentration. The asteroid belt marks a transition in the inward structure of the solar system. Beyond it lie the giant planets and the broad cold outskirts. Within it begin the more compact inner worlds. Yet within its own region, the belt is complete in meaning. It is the realm of interrupted formation, preserved fragments, ancient collisions, and compositional variety. Stone, metal, and carbon-rich material circle the Sun in wide separation, each body carrying a small part of the early solar system's memory. In this quiet zone, the unfinished work of planetary building remains visible, not as failure, but as record. Inward from the asteroid belt, the solar system narrows into the realm of the inner planets, and the first of these encountered on the present path is Mars. This region feels more compact than the giant planet domain beyond it. Orbital distances are smaller, sunlight is stronger, and the materials that dominate us increasingly rocky rather than icy or gas-rich. Mars stands at the outer edge of this inner planetary family, a small terrestrial planet. Meaning a world made chiefly of rock and metal, it carries a thin atmosphere, polar ice, extinct volcanoes at great scale, deep canyons, ancient impact basins, and abundant signs that liquid water once moves across its surface long ago. In this inward transition, Mars marks the point where the solar system becomes more solid underfoot in imagination, more shaped by crust, stone, dust, and weather acting on land. Mars is much smaller than Earth. With lower gravity and a colder climate, its reddish colour comes from iron oxide in the dust and rock of its surface. Iron oxide is a compound formed when iron combines with oxygen, and in finely divided material it gives the planet its characteristic rust-red appearance. Seen from afar, Mars seems simple, a quiet red disk in the dark. Yet close observation reveals a world of striking diversity. There are broad volcanic provinces, heavily cratered southern highlands, smoother northern lowlands, dry channels, layered sediments, dune fields, and seasonal changes in frost and airborne dust. The planet is not geologically active in the same way Earth is today, but it preserves a long and complex history written across its surface. The atmosphere of Mars is thin, made mostly of carbon dioxide with small amounts of nitrogen, argon, and traces of other gases. Because the air is so tenuous, surface pressure is low, and liquid water is unstable under most present Martian conditions. Water on modern Mars usually exists as ice or as vapour, though salty brines may be possible in limited environments for short times. The thin atmosphere also provides little insulation, so temperature swings can be large between day and night and across seasons. Even so, the atmosphere is active enough to support clouds, winds, dust devils, and sometimes planet-wide dust storms that veil the surface in suspended fine particles. These storms do not carry the force of a dense Earth storm at the same wind speed, because the air is much thinner, but they can still redistribute dust on a global scale. Mars has seasons because its axis is tilted, somewhat like Earth's, though the details differ because of its longer year and more eccentric orbit. Carbon dioxide frost forms seasonally at the poles, especially during winter, building and then retreating as sunlight returns. Permanent water ice also exists within the polar caps, layered with dust and frozen carbon dioxide deposits in ways that preserve part of the planet's climate history. These polar regions are not merely white caps at the ends of a red globe. They are long-term storage sites of volatiles and records of changing environmental conditions over time. The surface of Mars contains some of the largest volcanic features in the solar system. Olympus Mons rises as the tallest known volcano, built over repeated eruptions across immense spans of time. Its great size is possible in part because Mars lacks the kind of active plate tectonics that on Earth move crust over mantle plumes and distribute volcanism more widely. Plate tectonics is the large-scale movement of rigid crustal plates over a planet's deeper interior. On Earth it shapes mountains, ocean basins, and earthquakes. Mars shows no present global plate tectonic system like Earth's. This allows volcanic centers to remain fixed relative to the crust for very long periods, building enormous structures. The Tharsis region, a vast volcanic rise, further shows how profoundly internal heat once shapes the Martian surface. Equally striking is Valles Marineris, a canyon system stretching thousands of kilometers across the planet. It is not one simple canyon carved by a single river, but a vast tectonic and erosional complex likely linked to crustal, stretching associated with the rise of nearby volcanic regions. Landslides, sedimentation, and perhaps local water-related processes modify it further through time. Its scale reveals that even a smaller planet can hold landscapes of extraordinary size when viewed across planetary distances. The most important scientific feature of Mars, however, may be the evidence for ancient liquid water, valley networks, delta deposits, minerals altered by water, and layered sedimentary rocks all indicate that water once stands, flows, or circulates through the Martian environment far more extensively than it does now. Observations indicate that early Mars is warmer, or at least intermittently wet enough in some regions to sustain rivers, lakes, and groundwater activity. it remains uncertain how long such habitable conditions persist and whether they are globally continuous or episodic. What is known is that Mars once has a more water-active surface than the cold, dry world seen today. This makes the planet central to questions about planetary climate evolution and the possible emergence of simple life beyond Earth. Mars also possesses two small moons, Phobos and Deimos. They are irregular in shape and dark in appearance, more like captured small bodies or heavily altered remnants than like large round moons. Their exact origin remains uncertain. One possibility is capture of asteroid-like objects. Another is formation from debris produced by a large impact on Mars. Whatever their origin, they add a modest local system to the planet's surroundings, Phobos, the larger and closer moon. Orbits so near Mars that tidal forces gradually draw it inward. Over long spans of time, it is expected either to break apart into debris or to fall onto the planet. Moving inward from Mars toward the region of Earth, orbital spacing becomes tighter and sunlight stronger. The solar system's materials become less dominated by volatile ices and more by rock and metal. Small body populations persist here as near-Earth asteroids, Mars-crossing asteroids, and occasional comets entering from farther out. But the prevailing identity of the region is planetary and terrestrial. It is a zone where surfaces can be imagined as ground rather than cloud tops, where crusts preserve impact scars and ancient flow features, and where atmospheres, if present, are shallow veneers over solid worlds. Above and below the main plane of the solar system, Mars and the neighbouring inner objects still follow the broad flat order inherited from the original disk, though not in perfect alignment. Their orbital inclinations remain modest compared with many outer scattered bodies. The inner system therefore appears flatter, more settled, and more tightly arranged than the distant regions beyond Neptune. The thickening seen in the scattered disk gives way here to a more concentrated family of rocky worlds. This inward transition through Mars to the inner worlds changes the texture of the solar system. The vast emptiness and frozen remoteness of the outer regions recede. In their place come shorter intervals between planets, stronger light, warmer surfaces, and landscapes made of basalt, dust, ice, and ancient sediment. Mars stands as the outer threshold of that stony realm, a cold desert planet holding the memory of water, weather, volcanoes, and a deeper past when conditions differ greatly from those of the present. In this region, the solar system begins to feel less like a distant arrangement of orbits and more like a family of actual worlds. Inward from Mars, the solar system reaches the orbital neighbourhood of Earth, a region that is small compared with the gulf between the outer planets, yet rich in structure, motion, and practical importance. This is not only the zone of Earth's own orbit around the Sun, it also includes the Moon, the space through which near-Earth asteroids pass, streams of dust left by comets, and a changing environment of radiation, magnetic influence, and human-made objects circling close to the planet. In this part of the solar system, distances become modest by planetary standards, and the relationship between Earth and surrounding space becomes direct. The region is not empty around Earth. It is layered with natural bodies, transient visitors, and orbital paths that cross and recross in steady, lawful motion. Earth travels around the Sun at an average distance of 1 astronomical unit, completing one orbit in 1 year. This path lies within the general flat plane that defines most of the solar system, though with a small inclination relative to the average orbital plane of the planets. Around Earth itself circles the Moon, the most prominent local companion of any inner planet. The Moon is large relative to Earth's size, much larger in proportion than the small moons of Mars. Because of this, the Earth-Moon system is not well described as a planet with a tiny attached satellite. It is better understood as a paired system in which the common centre of mass lies inside Earth, but not at its exact centre. This creates a subtle shared motion, as both bodies orbit the Sun together while also circling their mutual centre. The Moon shapes this neighbourhood profoundly. Its gravity raises tides in Earth's oceans, slows Earth's rotation gradually over long spans of time, and stabilizes the tilt of Earth's axis more effectively than would otherwise be the case. This stabilization helps moderate long-term changes in climate by reducing chaotic shifts in axial tilt. The Moon itself is a rocky world without a substantial atmosphere, preserving a surface marked by impact craters, dark volcanic plains, bright highlands, and layers of dust called regolith, the loose broken material covering much of airless bodies. It reflects sunlight strongly enough to dominate the night sky and remains the nearest large object beyond Earth. The origin of the Moon is best explained by the giant impact model. In this view, early in solar system history, a Mars-sized body collides with the young Earth, and debris from that event later gathers into the Moon. Observations of lunar rocks, Earth-Moon composition, and orbital dynamics strongly support some version of this model, though details remain under study. What matters here is that Earth's immediate neighbourhood is shaped by a past event of enormous consequence. The Moon is not simply a captured object passing nearby. It forms with Earth's later history and becomes part of the long-term structure of the local region. Earth's gravity also defines several useful zones in nearby space. One of these is the Hill sphere, the region around Earth where its gravity dominates over the Sun's gravity for the purpose of holding satellites. This region is not a hard shell but a practical boundary for orbital stability. Within it, natural and artificial satellites can remain bound to Earth. The Moon orbits within this larger gravitational domain, and many human-made spacecraft do as well. Closer to Earth are orbital bands commonly called low Earth orbit, medium Earth orbit, and geostationary orbit. These are not natural layers in the same sense as a planet's atmosphere, but they are real dynamical regions in which orbital speed, altitude, and purpose differ. Thousands of satellites now occupy these paths, making Earth's near-space environment partly natural and partly technological. Human-made objects do not define the astronomy of the solar system as a whole, yet near Earth they become part of what is actually out there. Satellites provide communication, navigation, weather observation, and scientific measurement. There is also orbital debris, fragments from collisions, explosions, and discarded hardware. This debris is not dense enough to form a visible cloud around the planet, but it poses a serious practical risk to spacecraft because orbital speeds are high. Near Earth, therefore, space is not only a scientific setting, it is also a used environment, one altered by human activity while still governed by the same gravitational laws that shape moons and planets. Natural small bodies also pass through Earth's orbital neighbourhood. Near-Earth asteroids are objects whose paths bring them into the inner solar system, and sometimes close to Earth's orbit. They do not all pose danger, and most remain far away at any given time. But their existence means Earth does not move in complete isolation. Some are fragments delivered inward from the asteroid belt through resonances and long-term gravitational evolution. Others may be extinct comet-like bodies. Their compositions vary, including rocky, metallic, and carbon-rich types. Careful surveys track many of them because impacts, though infrequent on human timescales, are part of Earth's long history. Comets also enter this neighbourhood, especially from farther reservoirs beyond the giant planets. As a comet approaches the Sun, Solar heating causes volatile ices to sublimate, meaning they pass directly from solid to gas. This releases dust and gas to form a coma and tail. Earth sometimes crosses the trails of dust left behind by such comets, producing meteor showers. These showers are not random fireworks in the sky. They are signs that Earth's orbit intersects streams of debris spread along cometary paths. Tiny grains strike the atmosphere at high speed, heat the surrounding air, and produce streaks of light. In this way, even fine dust from distant icy bodies becomes part of Earth's local orbital environment. Earth's magnetic field adds another layer to this neighborhood. The magnetosphere is the region where Earth's magnetic field governs the motion of charged particles. It deflects much of the solar wind and traps some particles in the Van Allen radiation belts, zones of energetic charge particles held by magnetic forces. These belts are part of what lies around Earth in space, though invisible to ordinary sight. They matter for satellites, astronauts, and space weather. Space weather refers to changing conditions in near space driven mainly by the Sun, including solar flares, coronal mass ejections, and variations in the solar wind. Earth's orbital neighborhood is therefore shaped not only by gravity and matter, but also by electromagnetic interactions. Above and below Earth in the everyday human sense, the sky seems like a dome over one world. In astronomical reality, Earth's neighborhood is more like a three-dimensional corridor within the larger flatness of the solar system. The Moon's orbit is slightly tilted. Near-Earth asteroids can arrive from somewhat different inclinations. Artificial satellites occupy many orbital planes. Earth's magnetosphere stretches sunward and forms a longer tail away from the Sun. The region is not a simple ring or shell. It is a dynamically layered volume around a planet moving through solar space. This neighborhood is practical because it is home, but it is also scientifically revealing. It shows how a terrestrial planet exists within its immediate cosmic setting. Earth is not isolated by its atmosphere or by the Moon. It is connected continuously to surrounding space through gravity, radiation, magnetic fields, dust, and passing bodies. In this region, the solar system becomes intimate in scale without becoming simple. The orbital path of Earth, the close presence of the Moon, the crossing of asteroid and comet debris, and the layered magnetic environment together form the most familiar part of space, and yet a part that remains active, crowded in function, and fully embedded in the larger order around the Sun. At the center of the solar system lies the Sun, the one star around which all the planets, moons, asteroids, comets, dust, and distant icy bodies move. Everything described so far, from the scattered outer populations to Earth's near-space environment, remains bound together by the Sun's gravity and sustained by its energy. The Sun contains almost all the mass in the solar system. This is why the planets orbit it rather than the other way around, and why the system as a whole takes its shape from one central body. Yet the Sun is not only a gravitational anchor, it is a physical star, a sphere of hot plasma generating light and heat through nuclear fusion in its core, with layered internal structure and an outer atmosphere that extends far into space. The Sun is a main sequence star, meaning it is in the long stable phase of its life during which hydrogen fuses into helium in the core. Fusion is the joining of lighter atomic nuclei into heavier ones, releasing energy in the process. In the Sun, the core is so hot and dense that hydrogen nuclei can overcome their natural electrical repulsion and combine through a series of reactions. This process converts a small amount of mass into energy, as described by the well-known relation between mass and energy in physics. That energy then works its way outward through the Sun's interior and eventually leaves the surface as light, heat, and other forms of radiation. The Sun does not burn like wood or coal in air. It shines because of fusion deep inside, a process possible only under enormous pressure and temperature. The core occupies the innermost part of the Sun. It is the only region where fusion occurs at a high enough rate to power the star. Temperatures there reach about 15 million degrees Celsius, and the pressure is immense because the weight of the overlying layers presses inward. This inward squeeze is balanced by outward pressure produced by the hot gas and the energy released by fusion. The balance between inward gravity and outward pressure is called hydrostatic equilibrium. It is what keeps the Sun stable over long spans of time. If gravity alone acted, the Sun would collapse. If outward pressure greatly exceeded gravity, the Sun would expand. Instead, the two remain in balance, allowing the star to shine steadily for billions of years. Outside the core lies the radiative zone. In this region, energy moves outward mainly by radiation. That does not mean the region is empty or transparent in a simple sense. The solar material is still dense plasma, and photons are repeatedly absorbed and re-emitted by particles as they move outward. A photon is a packet of light energy. Because of the enormous density, this journey is not direct. Energy produced in the core takes an extremely long time to migrate outward through the radiative zone. The exact timescale depends on the model and the way the transport is defined. But what matters most is that the path is slow and indirect. The sunlight reaching Earth today comes from energy generated in the core long ago, though the final release from the visible surface happens only after that long internal transfer. Farther outward lies the convective zone. Here the solar plasma becomes opaque in a way that makes radiation alone less efficient for carrying energy. Instead, hot material rises, cools somewhat, and then sinks again in a pattern called convection. This is similar in principle to the circulation in boiling water, though the Sun is of course a far more extreme and complex plasma environment. Convection creates cellular patterns visible at the surface, where bright rising regions and darker sinking edges appear on smaller scales. These patterns are called granulation. They show that the visible surface of the Sun is not still. It is constantly shifting as hot plasma rises from below and cooler material descends. The visible surface is known as the photosphere. This is the layer from which most of the Sun's visible light escapes into space. It is not a solid surface, but it functions as the apparent boundary of the Sun because deeper layers are too opaque to see through directly. The temperature of the photosphere is about 5,500 degrees Celsius, much cooler than the core but still hot enough to emit the broad spectrum of sunlight. Sunspots sometimes appear there as darker regions. They are darker only by contrast, because they are cooler than the surrounding photosphere, not cold in any ordinary sense. Sunspots are linked to strong magnetic fields that locally inhibit convection and alter the transport of heat. Above the photosphere lies the chromosphere and then the corona, the outer layers of the solar atmosphere. The chromosphere is a thinner layer visible under special conditions, while the corona extends outward as a vast, tenuous outer atmosphere. One of the quiet puzzles of solar physics is that the corona is much hotter than the photosphere beneath it. Observations show temperatures of millions of degrees Celsius in the corona, even though the visible surface is much cooler. The leading explanations involve magnetic processes and wave heating, but the detailed balance remains an active area of study. What is certain is that the Sun's atmosphere does not simply cool with height in a smooth way. It becomes more rarefied and yet, in energetic terms, much hotter. From the corona flows the solar wind. the continuous stream of charged particles that fills the heliosphere described earlier. This means the Sun does not end at the visible surface in a practical sense. Its influence extends outward through magnetic fields, particles, and radiation across the full breadth of the solar system. Solar activity rises and falls in an approximately 11-year cycle marked by changing numbers of sunspots, solar flares, and coronal mass ejections. A solar flare is a sudden release of energy from magnetic activity. A coronal mass ejection is a large expulsion of plasma and magnetic field into space. These events affect planets, magnetospheres, radiation conditions, and the outer shape of the heliosphere itself. The Sun is stable over long times, but it is not inactive. The Sun's composition is dominated by hydrogen, with helium as the next most abundant element. Heavier elements make up only a small fraction of its total mass. Yet that small fraction is crucial because it reflects the chemical history of earlier generations of stars. The Sun forms from gas already enriched by older stellar processes, and the planets form from the remaining disk around it. In that sense, the Sun is both the beginning of the solar system and part of a larger galactic cycle of matter. Its light allows life on Earth, its gravity orders the planetary system, and its plasma environment shapes the space between the planets. At the innermost point of this long inward path, what lies at the centre is not emptiness, not a fixed fire in the ordinary sense, and not a simple glowing ball. It is a self-gravitating star, layered from core to corona, converting hydrogen into helium and balancing its own enormous weight through the pressure of hot plasma and fusion energy. The solar system, from its farthest icy remnants to the orbit of Earth and beyond, exists because this star forms and remains stable. At the centre, everything returns to the Sun, the quiet and immense source around which all other regions find their place. The solar system settles into stillness when all these regions are held together in one calm view. Far beyond the planets, the faint interstellar medium presses softly against the heliosphere. Within that broad solar boundary, distant icy bodies continue their slow revolutions in darkness. Nearer in, the giant planets hold their moons, rings, storms, and magnetic fields in steady motion. The asteroid belt remains a scattered record of unfinished formation. The inner planets circle in brighter light, their rocky surfaces shaped by heat, impact, and time. Earth moves among them with its moon, its magnetic shelter, and its narrow band of living surface. At the centre, the Sun continues its quiet work, turning hydrogen into helium and sending energy outward across the whole system. Above and below the solar system, the same deeper pattern remains. There is no true ceiling and no floor in space, only structure relative to the broad plane of the galaxy and the flatter disk of planetary orbits. The Milky Way thins away from its mid-plane. Nearby stars remain far apart. Gas and dust remain delicate and sparse. The solar system keeps its place among these larger arrangements, neither central nor separate, but gently embedded within them. What appears from Earth as a sky of points and darkness becomes, when followed patiently inward, a layered physical system. Its boundaries are made not only of orbits, but of particles, pressure, gravity, light, ice, stone, and plasma. Its outer reaches are quiet and cold. Its inner regions are brighter and denser. Its centre is warm beyond ordinary measure, yet balanced and enduring on the scale of a star's life. In that order there is no abrupt edge and no hidden divide. There is only one continuous arrangement of matter and motion, widening into the galaxy and narrowing toward the sun, it remains immense, structured, and calm.